Okay, so today's lecture is about the convolution. So today is Friday, February 2nd. So the reading from page 40 to 50. And Monday it will be due date for homework number 4. And in Wednesday, the MATLAB 2 project, and also homework number 5. Remember, homework number 5, no submission, so don't worry about the submission. But make sure to practice the problem because these are important on the exam. So there will be MATLAB 2 and homework number 4. Then Friday, the readings are in page 40 to 58. Any question? Okay. So let's start. So the convolution. Last lectures, we discussed a lot about the impulse response, step response, ramp response, and I mentioned if there is other type of inputs, we try to make it similar to impulse response or in terms of impulse, ramp, and step response. But not every function like this. So how can I solve or to make it generic for any inputs? And we said the answer is the convolution. So for any LTI system, and we know LTI is linear time invariant, when we have x of t, the output y of t for any LTI system, and for any input x of t, no matter what it is, it will be the integral between negative infinity to infinity, x of tau, h of t minus tau d tau, where h of t is the impulse response. So we realize for any inputs, try to find the impulse response first, then do this integration. X of tau, h of t minus tau d tau, then you can find the impulse, or you can find the response no matter what it is. So here, actually, we can find the outputs by finding the impulse response. Find the response first, then you can find any response, whatever what it is, what's the input is. Now, we can make a shortcut for this equation, so we can say y of t will be x of t star h of t. So this is the same thing, you get equals to negative integral negative infinity to infinity, x of tau h of t minus tau dt. This is the same. So as a shortcut, we denoted it by star, or that star. So this rotate, or this is called convolution. And this notation is a star. It is not product, it's not dots, it's not cross, so it's not signal multiplication. So just understand this symbol as just other, unique symbol, something different. It's not product. So it's not, does not mean that's x times h. It's x convolution with h, or x convolved with h. This means, again, the integral between x of tau, h of t minus tau d tau. Okay? Sometimes, some people, again, we can write it as x of tau, star h, x of t, h of t. Some, maybe other references, they write it as star, then there is a circle, h of t. Whatever, you can put the circle or not, just focus on the star. This is the same notation. Okay? Again, this is convolution. Now, the question is, how we get this result? How we say it will be x convolved with h, or it will be x of tau, h of t minus tau d tau. How we get this result? What's the proof? Here is the proof on the right. So the proof. For all system, we have LTI system here. Then, whenever we have delta of t, it will give us h of t. We are all agree on this, right? Now, we know, since it's LTI system, LT or TI means time invariance. So whenever we say delta of t minus tau, it will be h of t minus tau. Why? Because it's time invariant system. Is this correct? Now, here again, it's LTI system. Try to multiply by x of t. So x of t, delta of t minus tau, x of t, h of t minus tau. This is because it's scalable. LTI system, since linear, one of the linear properties is scalable. And this is LTI. Now, let's do the integration in both sides. Here is LTI. Let's do the integration in both sides. So the integration x of t, x of tau, delta t minus tau, to negative infinity to infinity, d tau. This will be here the integration negative infinity to infinity, x of tau, h of t minus tau, d tau. Also, to avoid confusion, I'm going to just draw this as x of tau. Just make this correction. Here, x of tau. Okay. So, we did this integration. Why we did this? It's additive. So, because now it's linear, then these properties are true because it's linear. Now, let's look at this integration for the inputs integration. The integration, negative infinity to infinity, x of tau, delta t minus tau, d tau, it will be here, tau equal t, therefore this will be substituted here. So this will yields to be x of t. Because delta function, we know whenever we have f of a or f of x times delta t f of t times delta t minus tau equal to f whenever we have integration d tau is equal to f of t, which is the same as what we did here. Therefore, as a result, we will say for that LTI, we realize this is x of t, so the output is between negative infinity to infinity, x of tau, h of t minus tau, d tau. This is the same as the output. And that's the convolution. Okay? So basically what we did the explanation, time invariance, then make multiplication of x of t side and do the integration, and do the integration for the inputs, it will be x of t, that's how we did it. So as a result, for any LTI system, the output y of t is found by convoluting the inputs x of t with impulse response. So we can find the output by knowing the impulse response first, then do the convolution between the impulse response, which is h of t, and the input x of t. Okay? In other words, we will say that LTI system is uniquely determined by its impulse response. It is h of t. So it can be denoted as h of t such that it is x of t. Here's what it is. Keep in mind the convolution x of t, h of t. This does not equal when I say x of t times h of t. And it does not equal when I say x of t product cross h of t. They are not. It is something different. What it is equal, which is equal again, the integration negative infinity to infinity, x of tau, h of t minus tau. So just keep in mind that star convolution is something different that we used to know before. Okay? Now, let's discuss some convolution properties, some important properties for the convolution, which is, I think, around 10 to 11 properties. So, convolution properties. These properties are important. So, remember that the convolution, we have x of t. Here is LTI system, y of t, which is x of t convolved with h of t. Now the properties, the first one, which is it's linear. What does this mean? Assume x of t equals ax1 plus bx2. Assume y of t equals to a y1 plus b y2, and we know x, or actually y, equals x convolved with h, x of t convolved with h of t, like this. X of y of t equals to x of t convolved with h of t. Now let's substitute x of t as ax plus bx. This yields to be ax1 of t convolved with h of t plus ax2 of t convolved with h of t. Okay? That's how we do, because it's linear, then we can distribute it. Now, another property, or the second property, time shifting. So time shifting, whenever we have y of t equals to x of t convolved with h of t, here is no time shift. But if we have, for example, if we assume we have x of t minus t1 convolved with h of t minus t2, this yields to be y of t minus t1 minus t2. So you will include both. You will include this one, t1 and t2, you will include it here. Okay? This is important. This property is very important. Here's an example. Example, I can write it on the other page. Example for the time shifting. assume you have x of t convolved with delta of t minus tau. This yields to be convolution with delta, with x will remain as x, then it will be t, then you will put minus tau. So here, whenever we have x of t, we'll make delay by tau. This yields to be x of t minus tau. So whenever we have, again, x of t, and we have delta t minus tau, it will be x of t minus tau. So this is delta in convolution, this is the summary, delta of t minus tau in convolution means delay by tau. Okay? This is important result. Let's go to the third property. Is this clear? So far so good? Third property, cumulative. It's cumulative. What does cumulative mean? This means whenever we have x of t convolved with h of t, it will equal to h of t convolved with x of t. They are equal to each other. So, what does this mean in integration? This means the integration from negative infinity to infinity. X of tau, h of t minus tau, d tau equals to integration from negative infinity to infinity, h of tau, x of t minus tau, d tau. So they are both equal to each other. So no matter if we make the shift at h, shift at x, they're both the same. How this looks like in the log diagram. So if, for example, we used to write the convolution as h of t, here y of t, and this is h of t. That's what we used to write. So because here x of t convolved with h of t. And the same thing, we can write it in the opposite, which is we can let the input as h of t, while x of t is at the box. So this means y of t equals to h of t convolved with x of t, and both of them are equivalents. So they're equivalent to each other. Okay? So if you do the integration first, h of t or x of t, they're equivalent to each other because it's cumulative. Property number 4, which is distributive. These properties are important to understand because we will use this a lot in our convolution. Actually, convolution topic, this is the most difficult thing in the sequence course. This is just a procedure for information. And later it will be easy. Okay, whenever I have x of t convolved with a h1 of t plus b h2 of t, using the distributive property, you can just make the convolution for both sides. So, like what you do, like what you do in multiplication. So you will do this one with this one, and this one with this one. So the first term and the second term. So let's do it with the first term. So it will be ax of t, a is constant, that's why I make it this way, convolved with h1 of t plus b x of t convolved with h2 of t. Okay? This is the distributive property. And distributive property looks like how we can do it, which is something like what we do in parallel systems. So here, x of t goes to, here is h1 of t, then goes to h2 of t, then both of them come to a sum. So we will something together to get y of t, which is x of t convolved with h1 plus h2. Okay? And if you want to multiply by product A or B, you can multiply. So we see here Hurley connection, like addition here. Okay? Does it make sense? Now, property number 5, associated. Associated. Okay. So associated means whenever we have x of t convolved with h of t convolved with, here's h1, here's h2. So when we do this kind of convolution, we have multiple convolutions like this one. So we need to calculate one of them or two pairs, then let's do with the third. So basically you need to choose. Let's do convolution with x1 and h1 first. After that, their result we will do it with h2. Does it really matter if I do the convolution with x and h1, then do the rest with h2? Or how about if I say, let me do the convolution h1 with h2, then I will do the result with x. Both of them are correct. So no matter about the order, they can be fine. So here, this means whenever you start, here is x of t, here is h1 of t, here is h2 of t, this will give us y of t. Or if you do like x of t, h2 of t first, then h1 of t, here's the arrows, this will give us y of t as well. Or when you say x of t, then h1 of t convolved with h2 of t, this should give you the same y of t. So all of them are equivalent. Which is y of t equals x of t convolved with h1 of t convolved with h2 of t. So we realize here we have series connection. So whenever you have the series connection or multiplication, so when we have this, it can be associative or distributive, so it can be fine. Okay? So far so good. Let's go to property number 6, which is causal output system. What does causal mean? Means output depends on currents or past inputs. It does not depend on the future. We already discussed this before. So every time it must be causal. So I would say, or the property here, LTI system is causal if and only if you know, this means if and only if h of t is causal. So if the outputs or the impulse response is causal, then the system is causal. This means the h of t equals 0 for all t less than 0. So in other words, h of t equals h of t times f of t. So this is how we can make it, this is causal. So I will say, in other words, when we have the convolution like the y of t equals to h of t convolved with x of t, so we will say causal equals, we'll make the convolution with causal convolved with causal. This will make the other part causal as well. So again, causal, let's assume you have this impulse response delta, or this impulse as impulse, and here is delta of t. This is entered to find the impulse response h of t, then the output h of t. In order to make it causal, it shouldn't, depending on the start at t equals 0, should depend on the present or past impulse. Okay? Or when you have any impulse runs at t equals 0, let's assume this is x of t, then here is x of t, here is h of t, then here is y of t. So let's assume the output y will start from t0, because it depends on the past or future. It will not depend on the past or present. It will not depend on the future. Okay? So if everything is 0, it will be 0. Yes?
For this, does x of t also be causal or causal?
Yes, if x of t is causal and h of t is causal, then it will be causal. Now, any other question? Let's go to property number 7. Which is convolution with delta of t. So whenever we have a convolution delta of t convolved with h of t, it will be the integral between negative infinity to infinity, delta of tau h of t minus tau d tau. Look inside the delta, make it equal to 0, so t equal to 0 or tau equal to 0. Therefore, it will be substitute. You will substitute h as t equals 0 or tau equals 0. It will be h of t minus 0. In other words, it will be h of t. Okay? Whenever we have delta of t minus t0 involved with h of t, it will be as when you do the integration negative infinity to infinity, delta of tau minus t0, h of t minus tau, d tau. Here this means you will substitute tau equal t0, so we will end up having h of t minus t0. Okay? So if you make the convolution only with delta, it will be the same function itself. So in summary, whenever we say delta of t convolved with h of t, it will be delta of t. I'm sorry, h of t, the function itself. It's simple, looks like you are multiplying by 1 or something like that. Whenever you make the convolution with delta, the function itself, no change at all. Whenever you do with t, delta t minus t0, the same function, but it will be shifted. So here this will be shifted by t0. Okay? Now, it's the same thing if we flip it. If we make x of t convolved with delta of t, it will be x of t. When we say x of t convolved with delta of t And let me add this. X of t minus t1 convolved with delta of t minus t2. This yields to be, since x convolved with delta will be x, there is t, then t1 minus t1 minus t2. Okay? Is this clear? So you need to understand these properties, and once you understand them, it will be easy. Property number 8. Let me give you, of course, a little bit right. Then we go to property number 8, which is the convolution with y of t. Then number 9, convolution with r of t. So we are trying to see the convolution with these three inputs, which is our most famous input, that is. So number 8, convolution with step function u of t. How we can do the convolution with u of t? Let's try see the equations. Then once we figure out the equations, we can use the result. We don't need to every time do the integration. Once we know it, then it will be, we'll apply it directly. The integral from negative infinity to infinity, x of tau, u of t minus tau, d tau. Recall that here, t minus tau equals 0, therefore, when tau equal to negative t. Or if we want to make it as addition or subtraction, this will make it as u of t minus tau will be 0 if tau less than t. Okay? Now, also we can do the integration. This integral, we can split it into integral negative infinity to t plus from t to infinity. So now let's try to do it. So basically, it will be the integration between negative infinity to t, x of tau, u of t minus tau, d tau, and then you add it to b1 of tau, tau, then plus the integral from t to infinity, x of tau, u of t minus tau, d tau. Now, the point is here, u of t minus tau from t to infinity. Here, when basically, in this situation, t is, or tau less than t, so this here will make it 0. And here, this will be equal to 1. Again, we can imagine this as a step input vice reversed. This is u minus tau, but the scale axis is tau. That's our axis, not t. And here, t. So t now is a point, it's a constant, while tau is a function. Then, when we do the convolution, this yields to be the integral from negative infinity to t, x of tau times 1, which is 1, d tau, and this will be 0, so plus integral of 0, t to infinity, d tau, this will make it 0. So we will end up having only the integral between negative infinity to t, x of tau, d tau. And this is again the convolution between x of t convolved with u of t. So what's the results? The interesting result about this, when we make a convolution of u of t, it will make it integral. So it will do the integral. So we can say that whenever, as a result, you apply x of t, convolve this with u of t, this will give you y of t, which is the integral negative infinity to t, x of tau, d tau. It is like, I would say, like ideal integral. So this means you are making the integral. And you know the integral symbol, which is this. So in LTI system, if you want to do integral, just put u of t. Apply it on u of t. Then u of t performance will do the integration. Okay? It looks like in the similar model of the diagram, it looks like you have a signal x of t and you have 1 over s, which is integral, or the integral symbol. Okay? 1 over s, I'm not sure if you are familiar with Laplace transformation, 1 over s means integration. Whatever, we will discuss this later about Laplace transformation, I think after 1 or 2 months. But the effects of u of t will make the integration. The effects delta of t, the same function. Whenever you say x convolved with delta, it will be x itself. X convolved with y, x convolved with u, this will make its integration. Okay? And when there is time, like t minus tau, this will make it phase change. Any question? Let's go to property number 9, which is convolution. With r of t. How can we make the convolution with r of t? As we know, r of t is the integral between negative infinity to t u of tau d tau, and it can be represented as t u of t. So in other words, we will say r of t, we can replace r of t to be as u of t convolved with u of t. Why u of t convolved u of t? The first u of t comes from the integral, the second u of t comes inside it. Okay? The first u of t comes from the integral, the second u of t comes from this. Okay? So this is now another representation for r of t with respect to u of t, and this is an important representation. U of t convolved with u of t. This will make it as r of t. So here is x of t. We have u of t here, then another u of t here. This will give us y of t, which is u of t convolved with u of t convolved with x of t. Okay? This is the same equivalent to the, here is x of t, and here is r of t, y of t equals to r of t convolved with x of t. In other words, you can replace r of t by u of t, so it will be u of t convolved with u of t convolved with x of t. Now, the first u of t is integral, second u of t is integral, therefore r of t looks like double integral. Okay, because u of t convolved with u of t. The first u of t will do the first integral, the second u of t will do the double integral. Okay? Let me go to the property number 10, which is integration. We're going to talk a little bit about integration. Integration. So, how we do the integral of the convolution? Like what? Assuming we have y of t equal x of t convolved with h of t. That's what we know about the convolution. How about if we do the integral? So if we say u of tau, then we make the integral negative infinity to t d tau. What will happen to the convolution? In the convolution, you will do only one side. So negative infinity to t, x of tau, d tau, convolved with h of t. Or you can do the integration for h of t. So it will be h of t convolve negative infinity to t h of tau theta. Okay? So it will be integral will be applied only at one term. Okay? When you do the convolution and you need to make the integral, make it only at either x or h, whatever you prefer. If you prefer x, make the integral for x. If you prefer y, make the integral to y. Okay? Now let's think about these scenarios. Let's think about when we have x of t, then we have h of t here, then we have y of t, then when we do y of t, u of t, what will happen? What do you expect the output will be? The integral, right? Because this one is integrated. So the output will be integral negative infinity to t u of tau theta. Let's see another scenario, which is when we have x of t here, then we have u of t here. This is integrator. So what do you expect the outputs here? It will be the integration from negative infinity to t x of tau theta. Then let's put h of t here. So the output will be the integral negative infinity to t x of tau theta convolved with h of t, and this is equal to the integral from negative infinity to t u of tau theta. And the other scenario, whenever you have x of t, then h of t convolved with u of t, this made the output to be as x of t convolved with the integral, because this is equal to the integral of negative infinity to t h of tau theta. Then here we will add it as negative infinity to t h of tau theta, which is the same as the integral negative infinity to t y of tau theta. So we realize number 1, 2, 3, they are all equivalent to each other. 1, 2, 3 are equivalent. Yes?
If you have more than two terms, do you still only apply the integral to one of the terms, so say 3 or 4 of them, that would be convoluted?
Yeah, that's a good question. You will apply only at one. If we have multiple, you will apply only at one. Okay, let's do any other question. Let's do a quick revisit. H of t, y step, y rank. We know the integral negative infinity to t h of tau d tau equals to y step. We know this, y step of t. We know the integral negative infinity to t of y step of tau d tau equals to y rank. We know this, and we know whenever you have delta of t, when you have h of t, the output will be h of t, right? That's what we do. So how about if we do this? the input is delta of t, then I inserted u of t. So u of t means integral. This means the output will be the integral of delta is u of t. Then how about when I do h of t here, the output will be y step, because the integral, or whenever you have the input h of t, input u of t, the output will be y step. The other thing, which is when we have the input delta of t and connect this to h of t, so the output will be h of t. Then when we do u of t, the output is the integral negative infinity to t h of tau d tau, which means the same as y step. So all of those two are equivalent. Then the same thing that we can do for the ramp. So in the ramp, y ramp of t equals integral from negative infinity to t y step of tau d tau. So let's assume this scenario. Whenever you have the input u of t, here you have y step of t, the output will be y step of t. Now, how about if we do u of t first, then convolve with u of t. With u of t means integrator. Integrator means the integration of u of t is r of t. And when we have r of t convolved with h of t, so the output will be, instead of u step will be y step will be y ramp. Because whenever you have the input r, it will be ramp response, right? So it will be y ramp of t, which is basically the integration from negative infinity to t y step. So this is another scenario when we have u of t and period y step of t. So the outputs will be as you have the inputs and you have actually this is h of t. U of t, and we have here h of t. So the output will be y step. Y step of t. Then we have y step of t with u of t. U of t is integrator. Doing the integration. So the integration of the step is ramp. This yields to y ramp. So make sure just to understand the concept. So it will be like negative from infinity to t, y step of tau theta. This means again, number 1 and number 2 are equivalent to each other. 1 and 2 are equivalent. Okay, so use just as an applications about how we do these things. Property number 11, which is the differentiation. We talked about the integration, now how about the differentiation? Integration, we will put it on one term. How about the differentiation when we do the derivative? So, assuming we have derivative on the first derivative by d by dt and x of t, derivative n of x, convolved with derivative of n with y, h of t. This yields to the sum of the derivative m plus n, m plus n. So this can be applied if there is no derivative, what's just n equals 0 or n equals 0. As a result, we will say when we have delta of t and we put the derivative d by dt, delta of t, this is equal to y of t equal the time derivative d by dt of delta of t, which is something we call a delta bar. So this thing is called delta bar of t, which is the derivative delta bar. Delta bar of t is the derivative of the impulse function delta. Delta of t. So, in other words, we will say when we have x of t and apply delta bar of t, this yields to be d by dt x of t. And this is something called ideal differentiability. So now we know two things: ideal integrator, ideal differentiator. Let me stop here and we'll continue on.